welcome to the Basement Podcast. I'm Daniil, and today I have Xander with me.
Hello.
And today we wanted to talk about first of all, not the existence of black holes, but just black holes in general, because they're very interesting. And we also wanted to talk about us, because in the first episode we didn't do that enough, I don't think. So,
We did a little bit, but yeah.
not enough. So that's something we want to do. And well, what do you want to start with, Xander?
I don't know. I mean, I don't know. It's a
Well, I want to talk about. I'm just gonna say why. Well, first of all, why I started the podcast and more about me. So, I have cerebral palsy, which is not so much a medical condition or a birth defect, but I was just born early, so I didn't develop.
Daniil is undeveloped.
Yes, I am undeveloped in the leg region. But so my legs are my muscles don't grow as fast as my bones do. And my muscles get very, very tight very easily. And so I ski and stuff. I ski. I can swim. I just had a surgery not long ago, about 3 months ago, corrective surgery because my bone was rotating. And I started the podcast because I felt like it was an outlet for me that I could. The fact that I have cerebral palsy does not change what I can do in a podcast, and that's what I really liked about it. So that's why I started, and that's why I wanted to do a podcast in the first place. And Xander, would you like to talk about yourself?
Well, first of all, I'm dyslexic, so in case you don't know what that means, letters and words will jump around on me sometimes, and
I mean, that happens to
things
me,
backwards.
but I'm not.
What?
That happens to me, but it's not as bad.
No, I have dyslexia, so it's bad for me.
Yeah, but again, I have that, but it's not as nearly as bad
Yeah.
as yours.
So, I do competitive robotics. For Hazlitt. I do a little bit of 3D printing. I build robots of my own. I play World of Tanks. I play Pokemon.
I like tanks.
Yep. Let's see, what else do I do? I used to play tennis. Let's see. Oh, yeah, duh. I play drums. I played drums for about, probably going on 7 years now. And I'm a percussionist at,
Our band.
Yeah, Okemos Middle School. Can't think of anything else right now.
If you haven't figured out already, we live in Michigan.
Yeah.
And yeah, I actually, just so you know, Xander, I want to join the robotics team. I've been so busy recently. AJ was in our last podcast. He's also on the robotics team. AJ said that I could still join, but I'm just wondering, can I still do that?
Not our team, because we're already so far into it. Hey, AJ's on my team, by the way. We're already so far into it that if you joined, you would have no idea what we were talking about. So, I mean, you could join. We had a team join just like our last meet, but they're a completely separate team, and they're doing something completely different. So, you'd probably be doing something like that.
But we wanted to talk about, because we had an argument at lunch, and I said, hey, this would be great podcast material. We were talking about
black holes.
Black holes, and first of all, what happens to matter when a black hole has completely imploded. The matter inside the black hole. Second of all, what was the second thing we were talking about?
What happens once it gets to the smallest point it can, I think.
Yeah.
That part of the matter thing, it might have been. I can't remember now.
Oh, yeah, and tachyon particles.
Oh, yeah, tachyons. Another theoretical particle. Supposed to be able to go faster than light. And,
no, it's... The theoretical law is that it always goes faster than light.
Yeah, well, a tachyon particle is supposed to be able to go faster than light, and that's why we have never found one, because theoretically, by the time you found one, it's already gone. You can't study them. But what our question is, what happens when you come in contact with a tachyon particle?
Yeah,
does it just go right through you, or is it so
because keep in mind, just so you know, not you, Xander, but the viewers, a light particle has no mass. So
actually, light is not a particle.
Light is a photon.
Light's a wave.
It's a wave. It's a photon. It's a type of wave. Actually, the notion that lights are particles is widely not... Well, it's not true at all, but it's widely fed. But light, again, goes straight through you or bounces off of you. So...
Well, if light goes straight through you, then you've got a problem. Light is a reflective wave, or a radiation, if you will.
It's something that you can see, of course, because that's the way you see.
Yes, because it reflects off of objects.
Yeah. And so, AJ keeps trying to call me. I don't want AJ on this podcast because he wouldn't understand the thing. Anyway, so we were talking about, and you can give your opinion in the comments if you'd like to, which you probably wouldn't, but what if with black holes, what happens when, it gets to its smallest point? And, again, if you don't know, black holes are just a star condensed to a very, 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 very small point. It may be...
Imploded star, basically.
Yeah, it's an imploded star. I don't know how big the center of black holes are, and keep in mind the center of black holes are theoretical, so it may not even be like that.
Oh, I just want to say something.
Yeah.
You know how people say, black hole, right? Well,
yep.
If you're going to be, really technical, you really technically should say... I just said technical twice, but who cares?
Yeah.
You should say black sphere. Because it's not... It's a sphere.
You go through... Well, yeah, because it's just a tiny planet, basically, that has so much gravity that, it can suck in light.
Yeah. Light doesn't bounce off of it. That's why you don't see what it actually looks like.
But we had this argument, but what happens if, light, when the black hole condenses completely, and the matter gets to its smallest point, its densest form, if you will. Does it turn into just pure energy, or is it I don't know, is it just completely, is it just, is it a wormhole, as you suggested?
Does it just or does it just go poof?
Yeah, is the matter destroyed, which is against the laws...
Against every single law in physics. You can't destroy energy, you can't destroy matter.
Yep.
But...
Matter can turn into energy, can't it?
Yeah, that's what... Well... Yes, you know how a fire works, right?
Yep.
Yeah, so... It like the fire burns the wood, which releases energy, which is actually what you're seeing with the flames, and then what's left over is the carbon. Actually, technically, matter can't be converted into energy. Matter actually contains energy. That's why when wood burns, it gives off heat. That's heat energy.
Because it's just the wood. Well, first of all, the wood isn't disappearing. It's just, again, turning into ash, turning into a different form.
Carbon.
And all of its energy and carbon is being burned off.
No, the carbon is what is left of it.
Well, it's not being burned off. Sorry, yeah, it's being exposed.
Yeah.
Can I quite literally say, ooh, burn?
I guess. I don't know.
But, like, it's just so interesting because, and that's something I love about theoretical physics. And, just space in general. So much of it is unknown that you have such, like, I guess it's a place for your mind to wander because you
have space to wander. Ha ha.
Funny. But it's something that's not proven. Something that isn't something isn't
theories constantly changing, yeah.
Yeah, it's constantly changing. The theory is constantly changing. You can create your own theory and research it and figure out if it's true or not. And then if it's not true, then you can just keep questioning. And that's what I love, because you can just ask more and more questions, and then you'll have more and more to think about. And that's also why theoretical physics, when you think about it, your brain fries in about 5 minutes.
Yeah, because it doesn't make sense most of the time.
Yep. Like, you have these supermassive black holes.
Which is what it's at the center of galaxies. Actually, it's
the
center of our galaxy. We have a supermassive black hole. Yep.
That's something that I think, isn't that the thing that's pulling our galaxy together? But it's also...
That's why a galaxy looks like a swirl, is because it's circling in and actually kind of
being sucked in slowly.
Being eaten by a black hole.
Slowly.
Yes, very slow.
But before we get sucked into a black hole, the supermassive black hole at the center of our universe, our sun will implode.
You mean our galaxy, right?
No, our galaxy. Our sun will implode, and then we'll be sucked into that black hole first.
Actually, our sun is more likely to go nova, because only usually red dwarfs are the most common star to implode and go black hole.
Which is the biggest type of star?
Our sun is just an orange star. I forget exactly what it's called, but it's an orange in the orange spectrum, and it's more likely to go nova. And
what's the biggest star? What's it like called? Not the specific star, but what's the biggest type of star?
I think red giants are the biggest, and they are the ones I think that can create supermassive black holes.
Yeah.
So black holes.
Yeah. And I actually am reading a book right now called A Brief History of Time. It's by Stephen Hawking. It's so, like, in depth, you could say, and it's so
mind blowing.
It's mind blowing, basically, like, because he knows how to speak in a certain way that you can understand it, and like there's sometimes, yes, he's Stephen Hawking, so you never know if you'll understand him.
Yeah, you kind of have to be a genius yourself.
Yep. But he in the first page he literally says, we don't think much of our universe and what what we solely depend on for life, and then he says in parentheses, except for children who don't know enough not to ask the important questions. Which is really true.
It's
because
true. We don't. Do you know the quote from I think it was Churchill? There are known unknowns, and there are unknown unknowns. So basically, what he's saying is, we have things that we know we don't know about, and there are things that we don't know
about anything. Like, we don't even know that it exists, basically.
So we can't ask questions about it.
Yeah, like, speaking of like curiosity and how kids, their mind, they think about stuff too much. You have, I don't remember. I think it was the person who discovered Halley's Comet. I know his last name was Halley, or Halley, but I don't. Edmund Halley, I think his name was. There was a comment, not a YouTube comment. Comment. Sorry, I have a cold. That people at that time thought that comets sprung, like, I don't remember what they're called, like famine and stuff like that, death, basically.
A big ball of ice brings famine.
Yeah, it shows you how much thinking about that something's going to happen can make it happen. Because, first, I just want to go on a little tangent here, but you can think about that something's going to happen, and you can subconsciously, like, help it happen.
Yeah.
You know what I mean?
Yeah.
Psychologically, that happens. Like, you accidentally, well, not accidentally, but subconsciously, you put that into action by yourself without noticing. And that's why those comets caused famine and stuff, because they thought, oh, this is going to happen. Well, it's bound to happen, so why? What did you say?
What you're talking about is actually called power of suggestion. It's basically where, or also sometimes referred to as Murphy's Law. If anything something can happen, it
will happen.
Likely will happen. Yes.
But that's like something that the human mind does without thinking about it. Like, and that's why, again, I love the human mind, and I love the way people think about things, because you can think about something completely abstract, and then you can test it, use trial and error to find if it's true, and then if it is true, then you ask another question, and another question, and another question, and another question, because you can't ever know everything, really.
It's impossible to know everything. You know why?
Because whenever you think you know everything, something new is discovered, or something new is thought of.
Everything changes, yeah.
Everything always changes.
Yeah.
And it's like, even Stephen Hawking himself wrote an article, I don't know how long ago it was, it's on Nature.com. He said, I didn't really read it in depth, but Xander, I think you did read it. He said there are no black holes.
No, he didn't say there's no black holes. He said that this is actually probably going to be a lot of gibberish to some of our less experienced listeners out there. But for those of you who do know what the horizon line of a black hole is, he says that there probably is no horizon line, and that it's just something that we somehow came up with. The horizon line is basically all the stuff you see around the black hole, the swirl, the thing that makes it look like, if you will, a galaxy or a
funnel type thing.
Yeah, exactly. And that that doesn't exist, and that it's just a black mass in space.
Then how did people think of it? How did they see it in telescopes?
We actually haven't seen a black hole.
Oh,
We've only have
I forgot about that.
we tracked a black hole that passed for a black hole very near to us, and it was a very actually quite a few like many solar systems away, but it was close enough for us to be able to monitor it and see it using computer programs. And what we saw was, I actually think it was a funnel. A computer actually showed a funnel.
Like a whirlpool, but then there was nothing. There was nothing around it.
Yes, and I'm actually going to change what I said earlier. A black hole is probably not like a sphere. Well, it may look like a sphere in appearance, but if you looked at it using something like probably actually you couldn't look at it using anything because it would just eat up lasers and radar. But if you could somehow look at it, they were, I don't know how they did it, but they were somehow able to get an image of a funnel. And this is the reason why. Once a star implodes, it actually, once it implodes, it starts to move. The black hole starts to move. The funnel literally pulls itself through space using, I think, using its extreme gravity and pulling on everything else around it.
It's kind of like an energy gun. He's pulling himself, or an energy grappling hook, so to speak.
And the reason it doesn't stop is because whenever it comes in contact with something, it
sucks it up.
Yeah.
Just like,
no,
nice meal.
It's like I eat stars for breakfast.
How long does it take? Do you know how long it takes a black hole to completely degenerate?
Oh, I have no idea. There's a theory out there that black holes don't actually degenerate and that they just become an extremely small point. Don't know what happens after that, but there's just a theory that it becomes an extremely small point.
And we were talking about it earlier. Like, you said it was a sphere, but you also said that it's like something comes out of the top and something comes out of the bottom. So it's like a funnel, but there's something inside that's holding it together.
Well,
if you look at proposed images of black holes, you see stuff coming out the top.
Well, that's just people's what people think about it. Hang on a second. I have a. You probably can't hear me, can you?
I can hear you.
Okay, good. I have a book that talks a little bit about black holes, and it shows that image. Hang on a second.
Yeah, but
so
it's what?
Actually, it doesn't talk about what that thing is. It just says that it exists. What I think it is somehow energy, because you can't really try to gravitate energy.
You can't do it.
Yeah, exactly. So my theory is the energy is coming through one side and just getting shot right out the other.
By the gravity. It's like
the Apollo. Think of the Apollo 13 moon mission. They used the moon's gravitational pull to whip around the moon and shoot themselves right back to Earth. That's kind of what this is doing. The energy is using the extreme
But I thought you just said that you can't gravitate energy.
Well, you can't hold it in one place. It's very complicated.
I actually come to think of it. Yeah, you can't hold it in one place because it's energy. It's moving all the time.
Yes, but I'm trying to explain something that really isn't backed up by really anything. There are technically the thing that you see going through a black hole sometimes, like in images and stuff, that probably doesn't actually exist.
The thing at the top?
The thing at the top and the bottom, that thing probably doesn't actually exist.
Why?
Because nothing comes out and nothing escapes a black hole.
Except for energy, you said.
Well,
But isn't light energy?
yeah, that's why I'm reconsidering. The
Yeah.
thing is, so I'm trying to explain that how it would go through one side and come out the other. It couldn't be energy. It couldn't actually be anything. Because nothing can escape a black hole, with maybe the exception of tachyon particles, because they do go faster than light, but we don't know.
But how much faster would they have to go to
Yeah.
escape a black hole?
Like, because a black hole, I don't know how much more gravity it would, an individual black hole would have compared to, our sun. But it is extremely massive. It has a lot more mass, you could actually say, because the star collapsed in on itself, making the gravity, okay, here's an example. If you took the sun or something, and you put it in a jar, you have yourself a black hole, basically, because you've just condensed all that space,
excuse me,
all that mass in that space into one tiny area, but you've also condensed all the gravity along with it. So for every bit, for that small amount, by how much you depleted by how much you depleted the star's size, it's been increased
in gravity and mass.
Yeah, it's basically you divide it by that much, but it's also multiplied by that much. So
actually, a good example of that, we had this project, where, or it wasn't a project, it was like a science lab. There was this hollow, I don't know, aluminum or steel ball, and then there was this something that weighed less, but it was a lot more dense and it felt heavier in your hand. Yeah. You remember that, Xander?
Yeah, I remember that.
And that's a prime example of that, because you take something, it weighs much, but it's spread out. But then you take something, you shrink it down to, you make it more dense.
The same material.
Same material, make it more dense, then you feel it more. And it has more of an impact on your hand because it's less spread out.
It's heavier, yes, but its mass doesn't change. The thing with a black hole is that at the start, the thing about black holes is when a star collapses in on itself, sort of theoretically its mass also collapses in on itself. So it's hard to explain, but a particle, I guess you could say the particles. The particles are literally
Could I just say it doesn't Ant-Man, it just shrinks itself?
It doesn't Ant-Man. Okay, yeah, that's a good example. Take Ant-Man, shrink him, but he's the same weight. Yeah. That's basically what happens with a black hole.
Yeah. So he's just a really, 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 really dense person.
Yeah. You take a let's say 500-pound football player and shrink him down to the size of an ant, but he still weighs 500 pounds. He's gonna hit better than any bullet you've ever known.
He's just gonna sink.
Yeah, he's just such density in such a small point. There's not a sidewalk that would hold him.
Yeah, he'd basically be like the mouse. They'd have to build a special road for him.
Actually, the rat, but yeah.
Sorry, the rat, yeah. But, speaking of which, and this was covered in a film theory episode. In Ant-Man, Xander, have you seen Ant-Man? The movie?
Yep.
Remember at the end when he enlarges the ant?
Yeah.
That's not physically sound. because
Well,
he doesn't
well,
change
then,
the mass.
well, when you think about it, then neither is a black hole. Because you're just
Yeah, but
doing.
he doesn't change the mass. He just changes the size, so it'll float away.
But it doesn't.
Exactly. So that's why the movie is wrong.
But then you're saying, but then technically the black hole theory is wrong. So think of it like this:
No, think about
if
it.
you do,
If
no,
you
if you've got
were
the
the size
opposite,
of a car, you would be very, very light. You could run and you could jump really, really high. Because all of your mass is spread out over a larger surface area.
well,
So,
but that's the
go on.
opposite if you get shrunk. Then if what you're saying is it's the opposite if you get shrunk.
Yeah, that's
You
what
get
I'm
shrunk
saying.
to half your size, you still have the same mass.
Yeah, but what I'm saying is that he took an ant and he made it about the size of a train engine. It would just float away, because I don't know if you know this, but if you drop an ant off of the Empire State Building, it'll be fine, because it's so light that it can't gain enough speed to damage itself. It's
Sorry,
like
my cat is purring.
so cute.
Yeah.
But it's like the way that the ant is built and the way that its mass is displaced, it can't, if you drop it.
Okay, if you punch this giant ant, doesn't that mean it would literally just cripple it? You'd
Basically,
literally
yeah.
put a
Well,
hole through it.
no, because it would be as, I don't know, actually. That's a good question. It
You
depends
don't
on if the
know.
material is the same as if it was very small. Because if it was as strong per, like, square millimeter or something, as it is when it's small, then if you punched it, you might get hurt. But if you punched it in and all the matter stays the same, it just spread out very easily, then yes, you would cripple it. You would just hit it and it would just, you'd poke it like a piece of paper. It would just start to, crumple up.
Yeah.
But yeah.
But
What?
here's the thing. So we're talking about black holes, right? Black holes collapse in on themselves. What if a star, like, instead of going black hole, I'm going to use a term that I probably shouldn't, but like went white hole, like it got bigger. I know what the theory of a white hole is. It's the opposite end of black hole where everything comes back out. But like a star, instead of becoming a black hole and becoming extremely massive, instead it becomes much, much larger, but keeps the same mass, and therefore
Actually,
we get
regarding that,
less
I have a
gravity.
question. How do black holes form again? I've been through this a couple times, but I forget what
It's
happened.
very
So I know the
theoretical.
star explodes.
It's very theoretical. There's a few ways it's theorized. The one I like the best is the matter collapse. Well, not the matter, but the gravity collapses in on itself, taking all the matter with it, and it just keeps collapsing, and anything within its gravitational field is pulled in with it, including light, and it because of the extreme mass of the star, once it has been condensed, the gravity becomes extreme, and nothing can escape it. It becomes and instead of emitting light, it eats light, basically.
Yeah. Like, again, a great book for I haven't read through it all, but I think it would give you a lot of things to think about and a lot of things like this that we've been talking about. Again, A Brief History of Time by Stephen Hawking. Again, I've started reading it. It's really good. And another one that I think, Xander, I don't know if you've seen it, but if you haven't, you would really like it. It's called Cosmos. I know Carl Sagan did one in 1980, but Neil deGrasse Tyson also did one in like 2014, and it's really, really comprehensive. This CGI is very, very in depth. You can kind of picture it as it would be in current scientific minds, how it would be put together, and everything that he talks about is like it's put into perspective in a way that you can understand it. Like he takes there's a thing that he does. It's he makes a cosmic calendar kind of thing, and it's 1 year, one calendar year, from the Big Bang up until today, and he describes the amount how minuscule the amount of time that we humans have been on Earth is compared to the rest of the universe.
Oh, I know. Well, even how long us humans have been on Earth compared to the dinosaurs. We've been on for like a tenth of the time that the dinosaurs had been on.
Not even a tenth.
Not even.
Because a tenth would be... Actually, how long were the dinosaurs? I don't even remember.
I don't.
How long were
I
the
don't
dinosaurs?
have. I don't have resources with me right now, but
Yeah. Yeah, but it's the... I'm trying to think. I'll actually look it up. Give me 1 sec.
Okay.
How long did
What?
the
Oh, you're not talking to me. All right.
dinosaurs apparently like 65 million years.
Yeah, that's
Not
what
that
I
was
thought.
65 million years ago. It says here between 230 and 65 million years ago. So let me do the quick math. That's what, like 165 million years. Basically. And to put it into perspective, we've only been on Earth for 200,000. So, if you think about it, a tenth of the the time that the dinosaurs lived on Earth would be 16.5 million years. A tenth of that would be 1.65, so on and so forth. And we're not even in the thousands, or maybe we're in the thousands, but we're not even in the hundredths of time, 1/100th of the amount of time that the dinosaurs lived. And the dinosaurs have only lived, what, like 1%, or even less than that, a tenth of the percent of the universe. So that really puts into perspective, like, how...
Not even a tenth.
Not even a tenth. How long the universe has been around. How long...
It's like 65 billion years or something. I don't know.
No, it's not 65 billion. It's 14 billion, I believe.
I thought it was 65 billion.
That's 65 million years ago the dinosaurs lived. But it's 14...
No, I said billion with a B.
Yeah, but it's 14 billion years that the... I think the Earth is 6 billion years old. But the universe is 14 billion years old. So...
Remember,
Yeah.
this is all theoretical.
All theoretical. From what we know, the Big Bang could have never happened.
And we could have just been around for who knows how long.
yeah, it's like that's how I think scientists who do not want to. As far as I know, Xander, you're also atheist, right?
Yeah.
As scientific logic goes, that's how people are like, how they think, how they explain the unthinkable. And you could think about it as Sheldon Cooper and his mom from Big Bang Theory, because his mom's a very, very religious person, but he's all hard facts and science. So it's like, it's the difference between those two things that, like, allow scientific prosperity, which is really, really something that I really don't understand how humans started to think about it. Like, human evolution has gone from just survival to making profits and, like, making an economy to freaking, having
What's
a
out
TV
there?
and having a TV and having YouTube and listening to this podcast.
Ah, yes, YouTube.
Of all things. It's like, there are so many people who go unnoticed. I don't even remember his name. I watched a documentary on him. It was the guy who created the first motor. Or first, I don't know what it was, but it was, again, something that was featured in Cosmos. If it weren't for him, he grew up in a very, very poor family and lived in a carriage, or lived, I think, in the slum of the 16th century, created this motor, and without that single person, we wouldn't have anything that we have today. We wouldn't have cars, we wouldn't have TVs, we wouldn't have, I don't know, computers, anything like that. Imagine the world without that.
Yeah, I know, right? Imagine you guys not having YouTube. Okay, so if I took away YouTube right now, probably a lot of people would die. It's like how
not a lot of people will die. A example of this would be, I've seen a post being circulated where, like, a teacher was trying to explain, not our teacher, but a teacher was trying to explain the importance of the Sugar Act and the intolerable acts to the colonists. And he put it this way. He said, what if you had to pay taxes every time you logged on to Wi-Fi? And apparently the guy who wrote the post heard two people say, I would literally murder someone. So, it's like, we become so dependent on what we have that you don't think about.
Yeah, well, we've become
complacent.
Well, more like we take advantage.
Yeah, no, I'd say we take for granted.
Yeah, take for granted. Yeah.
Cause imagine just trying to. Your main goal was not to, like, I don't know, get this research paper done by tomorrow, to find food to eat.
Yeah.
And, I mean, that's something that the world still experiences with poverty and
world hunger
and crime rates, which I feel like the amount of money and, like, resources that we spend on things that we don't need, really, could be, like, actually, not so much the money, but 40% of perfectly good food, both in homes and the industry, get thrown away. You know why?
It's a little something called expiration dates.
No, it's...
Actually, is that too, but...
There is that, but it's very, very rarely that it's not very rarely, but it's just very, very, very small part of the percentage of expiration dates. The fact of the matter is that people don't sell products because it's disfigured in some way. The food is good. It's a good plant. It's just, it was grown weird. There was something pressing against it. Something like that. And so people don't sell it. And then 40% of food gets thrown away.
Yep.
So imagine if we took all the food that we had that we threw away and we gave it to third world countries and places that don't have readily access to food and stuff. So it's really, mind-blowing if you think about stuff. If you think about not just, I don't want to use stuff too much, but
if you think about it a little bit,
if you think about just anything, there's almost always more to something than it seems. Like, I feel like that's become what this podcast is about. There's always more to space. There's always more to the brain. There's always more to history. There's always more to, there's always more to be done as well. Like, there's more stuff that you could do.
Yep.
And it's just, I don't know what to say, because I've kind of been ranting. Sorry, Xander, I've just been ranting and venting to you. But it's like, again, with our black hole thing, we could talk about it, and we did talk about it for about a solid 2 hours in total. We just sat there and we discussed that. And
we more have debated than discussed. But
we debated, yes. And you have the existence of tachyon particles, which I think we should talk about a little more in the podcast before it ends. But you have so much that human minds have thought of, and so much that things are, so much grammar, so many ideas and experiments and things that are deemed successful, and people think that's scientific fact. But unless you have photo evidence or solid, not abstract evidence,
people won't accept it.
Well, no, that's the problem. People do accept it.
Well,
except for if you're a scientist and you're part, and that was actually the motto of, I think, the English Royal Scientific Society: question everything, even if it's already accepted. Question everything. And another thing that I learned over the course of the past few months, there have been people who they've been murdered because they question ideas that are, ideas that are against the norm, and ideas that might be right, but people don't want to accept that. And then, 50 years later, after their death, people look at it and say, hey, he was right. We shouldn't have killed him. So it's a different story. It's a really different story when you look at science. And part of science, I believe, I think at least, is the fact that people are always, always, always going to be wanting
more
attention and money and everything. So even in science, which is supposedly, or in a perfect world, I use the phrase in a perfect world, it's just supposed to be about discovering and making human lives better. But there are so many things these days, even in science, that people are just, I guess, scamming the public into believing what they've done, even if they know it's wrong, so that they get money or resources and stuff. So it's a really, really something that
Politics.
What?
Politics.
Yeah. And then there's politics. So.
Well, that actually is part of politics. Is a lot of politics is scamming. You know what politics actually is mainly about? Like, not government and that kind of thing, but like politics. It's where you're trying to get people on your side that would not otherwise be on your side. So when you think about it, isn't that kind of like scamming? If you're telling someone one thing and they may think you mean another, and they do something for you, and then you're like, ha ha, you did this for me. Well, ha ha ha,
Yeah,
now I'm king of the world.
That's, that's the way people think. And I know we touched about this in last episode, and I don't want to sound like a broken record, but people say things, but then people who are like, yeah, that's a good thing, don't realize that most of the time that good thing has already been thought of. So it's a really complex world if you think about it.
Speaking of good things that have been thought of, let's talk about tachyon particles for like about 3 minutes, and I think our listeners are probably going to be about to drop dead.
Yeah. But so tachyons, and you can look them up on Wikipedia, it's a very, very theoretical particle, which, believe it or not, I was introduced through comics by. I was watching and reading a Flash comic, and that they use tachyon particles, and I was wondering, hey, is that a real thing? So I just looked it up, and apparently it's a theoretical particle. So, I'm sure as Andrew, I'm sorry, I've been talking a lot, but you're
fine.
I'm sure you have something that you want to say.
Well, as we said earlier, the main thing about tachyon particles, we don't know much about them, but we theorize that they accelerate at a faster pace than light. They're theoretical because they do accelerate faster than light, and
are they always accelerating?
Supposedly, yes. That's why we're not able to study them, because you can't see them like light. They're not. So they
don't have like a restrictive top speed.
No. Supposedly, they're like, they're not light though, because, well, you can see light, obviously. Otherwise, you're kind of blind. But you can't see tachyons because they are not reflective. They're not a wave, and they're not really an energy. We call them particles, but I don't think they're particles either. They're just.
I feel like
things.
They're a whole nother.
They're
part of another dimension. They're
their own thing.
Yeah, and I feel like maybe they're part of the space-time continuum. Like, the mix between the two, that might be something that's... Again, this is all very theoretical, and this is something that I'm just thinking about and thinking in my mind, oh, maybe that's true. Because if tachyons did exist, then you have... They can go faster, or they can rip through space, and they don't follow the laws of physics, because anything that can go that fast would be just tearing up reality, basically. And second, I bet you they dilate time so much that they're like traveling back in time, basically, or the field around them that is being affected the time is so dilated that time is going back in time. Time is going in reverse. You know what I mean?
Yeah, I see what you mean, but my theory is that tachyons are like they're well, first of all, I tried to do this. Define the speed of time.
Oh, oh my god.
You can't, exactly.
Yeah.
So that's sort of like a tachyon. if it goes faster than light, we don't know how much faster than light, but it goes faster than light, right? Well, first of all, we don't actually know exactly how many miles per hour light goes, but
we estimate it's around
E equals mc squared.
Yeah, or 186,000 meters per second, right?
I have no idea.
I don't know what it is.
Something like that, but
yeah.
But the interesting thing about a tachyon is you can't see it, you can't feel it. No one's coming. Nothing has come in contact with one, and
or else I bet you'd see a boom bigger than the Big Bang.
And yet we've theorized it. First of all, I'd actually like to know where this theory of a tachyon came from. Because when you think about it, it's actually completely bogus. You have literally nothing to back it up. At least for black holes, you have stuff to back it up because we've, quote-unquote, seen them before.
So, it's just so... Science is the greatest thing ever, I feel.
Science is the greatness.
And I will actually... You intrigued me, Xander. One thing I was thinking about earlier in the episode that I forgot about was how hot do you think it is in a black hole? Because in space, it's very cold, but in a black hole you couldn't reach absolute zero because everything is always being pulled in.
Well, see, that's tricky. Because there's two things that are possible. First one is it's the same as the space around it. The second is that because of the extreme friction of everything that has been pulled in, rubbing on each other because they're still being pulled in, maybe it creates some kind of heat. How much, I have no idea. But it might create some kind of heat because of the friction. Some amount of heat.
So anyway, but
we should be about done by now.
Yeah, we should be about done by now. I'm about to drop dead. Not just my viewers, but I'm about to drop dead. My brain is dead. So, I hope you enjoyed the podcast. If you did, then please leave a like and comment down below, and subscribe. But I will see you next time, and I hope that Xander will be here to join me. So, any final words, Xander?
Stay curious.
Yep, that's a good motto for anything, I feel. Stay curious. Okay, bye.
Bye.